Well, next thing that we need to talk about is operator overloading. All right, so is operator overloading a good idea or not? And actually, what is it in the first place? So what it is, what operator overloading is an operator that, that can be used for more than one purpose. Okay. So what's an example of that? Well, here's 5 plus 3. So we know that's going to give us 8. But also, here's hello plus world. It's probably my favorite operator overloading example because it's fairly ubiquitous in languages. We see it in lots of different places. So is this a good idea or a bad idea? Are you a good witch or a bad witch? Well, I think that's a religious argument. I feel like sometimes in some languages it makes a lot of sense. It's really convenient to concatenate strings using plus. And I think it's fairly well known that plus gets used for that. But you can take it too far because you can have sort of weird things happening. For example, what if I did this? What is 1 plus 1? Well, there's two possibilities. This could be 11 because we just concatenated the string 1 and 1 together. Or it could be 2 because the language says, oh, you're adding, those are two numbers, so you're adding them together, so you must have meant 2. Or it could be, sorry, it could be the string 11, or it could be, oddly, just 11. It meant you were supposed to put those two digits together. So this depends on the language. So you want to be careful with that. It's also possible in some languages to do an incredible amount of operator overloading. You can have that plus operator in the language C++, mean anything you want as long as the operands are of a type for a class that you specified. So for example, you could have cat C, dog D, and you could say animal A equals cat, C plus D. So we just added cats and dogs together. And you're allowed to, in C++, you're allowed to redefine what that operator plus means for any operands of your choosing. Pretty crazy. I don't think that's particularly readable. I don't know what happens if you combine a cat and a dog. I'm not sure I want to find out either. So generally, try to keep it simple. Maybe just have that plus operator overloaded for strings and integers, but don't try to do anything else. Okay. So the next thing I want to talk about with regard to expressions is type conversions. So type conversions happen when you have when you have operands with a different type, with different types. Or you have an assignment to a different type. That's a type of operator. So that makes sense. So in these two situations, basically, you might need type conversion. So here's an example. What do you think is going to happen here? Int I equals, int I double f equals 30, I guess we'll call that d. It's not really consistent there. Double d equals 32.5. And now we say I equals f. All right. Well, if you paid attention in Java, Java says that this is an error. And the reason why is that an integer is 4 bytes, a double is 8 bytes, and trying to stuff an 8-byte number into a 4-byte number is not a good deal, not a good thing. And also, we're not allowed to have anything to the right of the decimal point when we have an integer, and trying to take that 32.5 and stuff it into an integer, we're going to lose that 0.5. Java says that's not cool. We're going to talk about the exact type of situation that we run into there in just a second, but Java can treat that as an error. C++, on the other hand, it'll let you get away with it. C++ is going to say that I is 32. So it's going to truncate that 0.5 and get rid of it. But let's take a look at a slightly different. So these two probably make some kind of sense. And you know in Java you can override this error, right? If you say int d, then Java will say, okay, you want me to do this, I'm going to take that 32.5, throw everything to the right of the decimal point, and then stuff the rest of the result into that integer I. So that's how you could get rid of that problem in Java. But what if I were to do this instead? Here's another language, dim I as integer, I equals 32.5. What is the value of I? Well, it turns out that I is going to get set to 32. I equals 33.5. I get set equal to the value of 34. I equals 34.5. I get set equal to the value of 34. I equals 35.5. Oh, sorry. You can stop there. Okay. So what the heck is going on here? This is really weird. This first statement looks like it makes a lot of sense. I equals 32.5, and then it becomes 32. Okay, we're throwing stuff to the right of the decimal point. But I equals 33.5, I gets up to 34. Oh, it looks like we rounded up instead. And then 34.5, we're not rounding up. We're throwing away stuff to the right of the decimal place. This is very weird. So it looks like sometimes we're rounding up, and sometimes we're rounding down. That is crazy. So is there any method to the madness of how this language handles dealing with type conversion when we're converting from a rational number into an integer? And the answer is there is a lot of logic here. This is actually called the banker's algorithm for rounding. So I want you to think about this for a second. If we always threw away, if we're smart about rounding, in other words, if we had like 3.8, we're going to round up to 4. And we have 3.2, we're going to round down to 3. That makes total sense. When we're at 3.5, we don't know which way to go. Do we round up to 4 or do we round down to 3? So what the banker's algorithm says is that when you have, the banker's algorithm basically says round up or down to the nearest even number. All right. Now, why would you do that? Well, think about this. If we assume that we have a whole bunch of numbers in our database and that we have an even distribution of even numbers and odd numbers that have 0.5s in them, you know, not every number is going to have 0.5, but we have a whole bunch. Once we have hundreds of thousands of numbers, all right? And some of them have 0.5, and some of them are even, and some of them are odd, and it's pretty even distribution of what's even and what's odd when we have 0.5s. If we always round down when we have a 0.5 situation, then all of the numbers, as they're being converted to integers, are going to be skewed towards lower integers. So we're going to have a little bit of bias in our data. And if we always round up, then we're going to have a skew in our data where we have numbers that are slightly larger than what it should be. But if we round some numbers up and some numbers down, and we have 0.5, and we have this rule that it's I just round to the nearest even, whether that's up or down, and we have a nice even distribution of 0.5s between even and odd numbers, then they're going to cancel each other out, and we're going to end up with very little bias. So that's kind of interesting. So some languages do that when they're doing type conversion. Who would have thought? Now, there's a way to think about type conversions to build your expectation as to what's going to happen when you do a type conversion with in an expression, okay? And so that is, you want to answer the question of whether you're doing a narrowing conversion or a wide conversion. So a narrowing conversion converts the type to a new type that cannot approximate value. So if we go from a double to an int, that is a narrowing conversion. If we go from a double to a float, that is also a narrowing conversion. If the double is a really large number, that's definitely going to be a narrowing conversion. That's 8 bytes, that's 4 bytes. So we're going to lose some data. This is 8 bytes, that's 4 bytes. We're going to lose some data, plus we're going to lose that stuff to the right of the decimal point. That's going bye-bye. Okay. So some languages will allow you to do, will allow narrowing conversions with some automatic behavior, and some languages will not. All right, let's talk about wide conversion. All right, so this is where we're converting a type to a new type that can approximate a value. So if we have an int and we want to go to a double, things are going to work out okay. An int is 4 bytes, a double is 8 bytes. Anything an int can represent, a double can represent with no problem. If we go from a float, which is 4 bytes, to a double, which is 8 bytes, we're going to be fine. We're not going to lose any data or information. That's another way to think about it. A narrowing conversion, you're typically going to lose some information. A wide conversion, you're not going to lose any information. Now, conversions, these type conversions, can happen in a couple of different ways. So the type conversion can be implicit, which basically means that there's an automatic conversion. So you don't even ask for it, but it's going to happen. And then there's also an explicit, which we'll talk about in a second. All right, so here's how an implicit conversion gets set up. You have one. You have an expression with operands with different types. You have an operator that expects both types to be the same, both operands to have the same type. And so what will happen in this situation is that one or both operands are implicitly converted to the needed type. Okay, so how about an example? All right, so we've got this definition here, so let's do an example. All right, so if I say int I is equal to 2, double d is equal to 7.0, and then I have a double result, and I set that equal to d divided by I. So I have this situation where I've got a division operator, and the division operator expects that both operands are going to be doubles. That's what it expects. But, and D is a double, but I is not. So what happens to I is it gets implicitly converted to a double. You don't even ask for it, but the language will implicitly convert it to a double. So in this case, Java or C++ will convert it to double. So now we have 7.0 divided by 2.0 instead of 7.0 divided by 2, and that's going to give us 3.5, and that's the result that we are going to expect. All right, so let's look at another example where this happens. So what if I have int I is equal to 2, and int 2, and int j is equal to 7, and I've got an expression that says double result is equal to 7 divided by 2. Now, is there an implicit conversion that happens here? I'm going to take a moment to think about it. So the answer is yes, there is. So here's how this happens. So we take 7 divided by 2. This operator expects ints. All right, it expects that the operands are ints. Well, 7 is an int, and 2 is an int, so that's good. So the result of this expression, 7 divided by 2, is going to be 3. The problem is, though, we now have this operator here, this equal operator, or the assignment operator, and the assignment operator has a double on the left-hand side, result, and an integer on the right-hand side, that 3. The assignment operator is expecting a double. because ultimately the end result of the assignment is going to be in a double. So we have a problem. This 3 is an int, and we can't take an int and stuff it into a double. So what we're going to do is we're going to convert that int into a double, 3.0. So this is an implicit conversion. And that 3.0 then gets assigned to the result. So in the end, we end up with a result equal to 3.0. So that's an example of an implicit conversion. And this process of doing the implicit conversion is called type coercion. Okay, that's what's happening here when we do that implicit conversion. It's called type coercion. So a way to think about type coercion is, here's this 3 that's hanging out, that it's a happy little integer, and the language basically says, come on, 3, you don't want to be an integer. It's no fun being an integer. What you want to be is a double. And the 3 goes, all right, I'll become a double. So it becomes a 3.0. So that's called type coercion. Okay. Let's take a look at explicit conversion. So we just talked about implicit or automatic conversion, but there's also an explicit conversion. So an explicit conversion allows the programmer to force a type conversion. And this is common with narrowing conversions. For example, here's an example in C++. We could say char C equals A, and then C out int unsigned char C. And what this would do is it would give me the ASCII value for the character A. All right, so we're taking a character, which is basically a byte. It's a byte. And we're converting it into an integer and then displaying it. However, if I did this, int I equals 65, and then I wanted to say C out char. Well, if I wanted to say C out I, what that would do is that would print out the value of 65, but I actually want to print out the ASCII value of 65. So if I say C out char I, that will print out an A. Okay, so this is an example of a widening conversion. We're going from a single byte to an int, which is 4 bytes. That's 4 bytes. And this is an example of a narrowing conversion where we're going from 4 bytes to 1 byte. So this is a widening, and that happens automatically. We don't get any grief from that. And this is a narrowing. Okay.